Assalamu alaikum. Uh, Today we will continue the factors affecting the rate of enzyme action. Last day we discussed the effect of temperature and pH, and today we will discuss the effect of substrate concentration and enzyme concentration. So let's see. Effect of enzyme concentration on the rate of an enzyme action. Okay. So to investigate the effect of different enzyme concentrations on the rate of enzyme action, we can do an experiment in the lab. But how do we do that? Let's see. I'll just briefly discuss an investigation which could be used to investigate the effect of enzyme concentration on the rate of enzyme action. For example, we can take 5 test tubes, empty test tubes. Okay. So these are 5 empty test tubes. In each test tube, we put same volume of hydrogen peroxide, H2O2. Okay, so same volume, same volume. Then what we do, we prepare different concentrations of an enzyme catalase. To get an enzyme catalase, we can use the potato extract. We grind the potatoes in distilled water, and a small volume of water may be added just to facilitate the grinding of the potato extract. But you see, otherwise, this we considered as 100% potato extract. Okay, so this will have a high concentration of enzyme catalase in it. So this has an enzyme catalase. Enzyme catalase. Okay. Then we prepare 5 concentrations of plant extract by using dilution method. We can use a simple dilution method, or we can use maybe a serial dilution method. But in this case, we prepare the 5 concentration by simple dilution. Okay. In simple dilution, what do? We take 5 beakers, 4, maybe 5 beakers or 4 more empty beakers. So this is the 100% plant extract. Okay. We take an empty beaker and we label it 80% plant extract. Then we take another beaker and we label 60% plant extract. We take another beaker and we label it 40%, and then we can take similarly a 20% and 0% plant extract. Okay, so we take another empty beaker and we write 20% plant extract. Now this is the stock solution that have been given. This is the given concentration, and this concentration is represented by C1. And the next concentration that has to be made, concentration to be made in this case, is C2. And what volume of this has to be added into this, and what volume of distilled water has to be added into it, this is what we can calculate. Now we will have to decide what total volume has to be prepared. We can take maybe 10 cm cube. So this total volume is V2, and this is 10 cm cube that has to be made. Okay. Now this is V1, the volume of C1 that has to be added up into it to make this V2 is V1. And we already know that formula applied here is C1 is equal to C2 V2. We know C1 from here, it is 100%. Then V1 is to be calculated. C2, this is to be prepared in this case. So this is 80. And total volume which has to be prepared is 10 cm cube. So we'll multiply it with 10. And V1 would be 80 into 10 over 100. So this cancels out with this, and we divide this 80 with 10. So that would give us 8 cm cube. So 8 cm cube of this solution and 2 cm cube of distilled water has to be added up into this to make the total volume of 10. And similarly, we can calculate it for maybe, this solution. And then for this, we can make calculations for these two. And this makes a table here. We will have concentration of plant extract / percentage. And here we have the volume of, if this may be represented with P, volume of P, which is V1 to be taken in cm cube, and volume of W to be taken with its units. This is cm cube. Okay. So this is table. If 100% plant extract has to be made, we will take 10 cm cube of this and 0 cm cube of this. If it is 80% concentration to be made, we will take 8 cm cube of this solution and 2 cm cube of this. If 60% has to be made, we will take 6 of this and 4 of this. If it is 40, we will take 4 of this and 6 of this. And if it is 20%, we made 2 of this and 8% of 8 cm cube of this. So these concentrations are prepared in these beakers. And then what we do, we take one of these test tubes from here. Okay. And in this test tube, which is placed at some temperature in a water bath, it has hydrogen peroxide already added into it. And what we do, we place maybe 1 cm cube of this plant extract or 100% plant extract into it with the help of maybe a syringe, or maybe we have a rubber bung fixed into it. This is a stopper fixed into it. And through one bent tube, a gas syringe is attached with it. Okay. This is the gas syringe. attached with it. And through another, we can have another tube or a syringe with a capillary tube or this nozzle attached with it. So with the help of this syringe, we pour 1 cm cube of 100% plant extract. And we start timer. And record the volume of oxygen collected here. This hydrogen peroxide will be broken down to water and oxygen by this enzyme catalase. So catalase, if it has, this is, plant extract contains a catalase enzyme, and this catalase enzyme will break down water into this hydrogen peroxide into water and oxygen. Oxygen will be liberated out of it, and that will be collected here into this syringe. And what we do, we record the volume of oxygen collected, record volume of O2 collected in 10 minutes after every minute. Maybe after every minute, maybe after every 30 seconds, maybe after every 2 minutes, so that doesn't matter. So at this end, in the first column, we write the concentration of plant extract, which is \% and then we write the volume of O2 collected. Okay, so we can do this experiment in the lab and we can record these results. Okay, so this is 100%, this is 80%, this is 60%, this is 40%, this is 20%, and we can record the volume collected. We can repeat this experiment with every this concentration. First, we have done with this 100% plant extract. Then we take the other test tube, okay, and we do it with 60%, 80%, then 60%, then 40%. So with every this concentration that we have prepared, we record the volume of oxygen collected here till 10 minutes, or maybe some specific time, 3 minutes may be taken. So that doesn't matter. So for 3 minutes after every 30 seconds. It is difficult to record after every 30 seconds in a lab for a student, but as a theory, we can discuss that after 30 seconds, the rate has been, this volume has been collected. Now, maybe the volume collected after 3 minutes in this 20% plant extract will be the least, and this will be the most. Okay. And as it is collected after every 30 seconds, we can collect the total volume, or as it is collected after every 30 seconds, so we can divide it into the first 30 seconds, then we have 60 seconds, then we have 90 seconds, we have 120 seconds, we have 150 seconds, we have 180 seconds, and we have 210 seconds. So this would give the progress of an enzyme action over a period of 3 minutes, and we record this volume after every 30 seconds. So these results can be assumed in this case, and if we plot these results on a graph paper, we will have a graph obtained this way. On an x-axis, we write the time. In seconds, and on y-axis, we write the volume of O2 collected And we, if carried out this experiment at, this is 30, 60, 90, 120, 150, 180, and 210. So we investigated the effect of lowest concentration of an enzyme or plant extract on the volume of oxygen collected over a period of time, and the volumes collected were plotted on a graph, and this gave us this graph, and this was at 20%, for example. Then we repeated this experiment at 40% plant extract. This is 20% plant. Okay, volume was kept constant, and then we repeated it, and we had this. Then we repeated it. This is 40% at 60. So we had this at 60%. So as the concentration is increasing, the volume of oxygen collected is increasing. Okay. And then we will have, at 80. And then we have at 100%. So you see, this is towards the end, after a very long time, the volume of oxygen collected will be the same as the substrate concentration have been kept constant, or substrate concentration, or the volume and the concentration of hydrogen peroxide at each, the concentration of enzyme has been varied, but the concentration of substrate has not been changed. So after the chemical reaction ends up, at each enzyme concentration, the volume of oxygen collected will be the same. So all these curves would, meet at same point somewhere after some time. So we don't need to know that. So this is how we will see the progress of enzyme action at different enzyme concentrations. Now, as we carry out this experiment, do you see at 30 degrees Celsius, or after 30 seconds, the rate of enzyme action at different concentrations of plant extract is different. Okay, so this is 80% and this is 100%. As the reaction progresses, the substrate concentration decreases. So instead of plotting, the rate of an enzyme action against the different concentrations of an enzyme or plant extract, we take an initial rate of enzyme action. Okay, so we can plot concentration of an enzyme or enzyme concentration. You see, we can start with 0. We can write 20. We can write, this is 40, this is 60, this is 80, and this is 100. So you see, we might have the different concentrations of enzymes in it, but as we have taken the plant extract to have catalase enzymes, so I'll write that the concentrations of plant extract here on x-axis. Okay, so this is in percentage. And here, instead of plotting the rate on y-axis, I'll take initial rate of an enzyme action. Why it is important to take initial rate instead of taking rate? Like in the initial possible time where we can measure the rate of enzyme action, the substrate concentration will be the maximum, and that would be the same substrate concentration. As the enzyme activity progresses, or the rate as the reaction progresses, the substrate concentration decreases, and for different enzyme concentrations, the substrate concentration decreases with a different rate. So we will have the different substrate concentrations at the different times. So that would give us the different rate if we take rate long after the chemical reaction has been started. So we will take the earliest possible time where we can measure the rate of an enzyme action, and that would give us the initial rate of an enzyme action. Initial rate of an enzyme action. Okay, so the rate calculated at the possible earliest time where the rate could be, or the product or the measurement, where the measurement could be made, is known as an initial rate of an enzyme action. You got it? So here we can measure this initial rate of enzyme action. Okay, finding the initial rate of an enzyme action. Here it is very simple to, to just draw a vertical line over this 30 seconds, and then a horizontal line here, horizontal to x-axis, which cuts at this y, and we can find this value from here, for the volume of O2 produced. This is the volume of O2 produced, volume of O2 collected here, and dividing this by this 30 seconds time, that would give us the rate. So rate will be equal to volume of O2 divided by this time where this measurement has been made, and the measurement has been possible in this case. So that will give us the rate. There is another way of doing it where we plot a tangent. So if this is time on this axis, this is 30. This is, this is, the time on this axis, and we have this 30, we have 60, we have 90 seconds, we have 120 seconds, we have 150 seconds, 180 seconds, and so on. This is time in seconds. And for example, this has been, the volume of O2 collected at some concentration. If we have to find the initial rate, we draw a tangent on this curve. The tangent is a straight line drawn with the help of a ruler, which touches at one point, maybe at this point. Okay, so with the help of a ruler, we draw a straight line. At both ends, it has the same length of this, the line. And then what we do is, we take this value from here, or we draw this, maybe this value from here. Okay, so we have two points here. One is this, and the other is this. So we take a difference of the volume collected from here, difference of volume of O2 collected from here, and from here we take the difference in the time, and rate can be calculated as difference in the volume from y-axis divided by difference in the time, the x-axis. Okay, that would give us the the initial rate actually. Now, if we plot the initial rate of enzyme action at these different concentrations of enzyme, a linear line or a straight line obtained that shows that provided the substrate concentration is provided, the substrate concentration is maximum or unlimited, infinite, unlimited, the rate will be linear to the increase of enzyme concentration. Now we might be asked to explain why, explain this graph by increasing the substrate concentration that increases the initial rate of enzyme action, and why do we get this linear curve? The reason is very simple, that as you are increasing the enzyme concentration, there are more active site available and there would be more enzyme substrate complexes formed, and that would have a higher rate of an enzyme action, right? So that's about the effect of an enzyme concentration on the rate of an enzyme action. Similarly, we can investigate the effect of substrate concentration, effect of substrate concentration on the rate of an enzyme action. Similarly, now we can take the same concentration of an enzyme, but we vary a substrate concentration. The rest of the other conditions like temperature, pH, and volume that are kept constant, and we record the volume of oxygen collected at various substrate concentrations. And then similarly, we calculate the rate of initial rate of an enzyme action at different substrate concentrations. And if we plot that on a graph, we will have substrate concentration on x-axis, the units, and we will have the initial rate, okay, on y-axis. And the graph obtained will be, you know, as we increase the substrate concentration initially, the rate increases, but at a very high substrate concentration, the rate becomes maximum, and that becomes, the curve becomes leveled off. Okay, so this maximum rate achieved is known as Vmax. So how we can explain this? We may have a question to describe the effect of substrate concentration, or to explain the effect of substrate concentration on the initial rate of enzyme action. So if it is to describe, you can simply write as substrate concentration increases, substrate concentration increases, the rate also increases. Okay, so this is and you can give a numerical quote here. What does a numerical quote mean? Numerical quote, or the reference that you can give, is from an x-axis, value from an x-axis, and value from y-axis. So that will be the numerical quote. In this case, I don't have precisely the values of substrate concentrations here, and I don't have the values here for the initial rate on this graph paper, on this graph, because this is a sketched graph. We can take the plotted exact values, and we can give this numerical reference here. But the next point is, from this concentration ahead, if further substrate concentration is increased, then the rate is leveled off, or this curve is leveled off and the rate becomes constant, fairly constant. Okay, so this is another point that we can write at very high substrate concentration, the rate is constant. Okay, so this is how we can describe this graph. Then we will have to explain, give reasons for that. To explain this, you can write more substrate molecules, more chances of collision between enzyme and substrate, and more ES complexes form, and higher the rate. So this first point can be explained this way. But why then this level off? Why then it becomes constant? Even if the substrate concentration is further increased, why this becomes constant? The reason being, at very high substrate concentration, when this Vmax is achieved, so you see this at this Vmax, 100% enzymes are involved in ES complexes. So at this substrate concentration and onward, 100% enzymes are saturated with the substrate molecules, active sites are occupied. All active sites are occupied by substrate molecules. So substrate molecules are queued up technically, waiting for their turn to bind into an active site and be converted into, to make enzyme substrate complexes and to be converted into the products. So as all the active sites of all the enzymes are saturated, so the rate becomes constant, or the rate becomes, or the curve becomes leveled off, right? So that's about the effect of substrate concentration. And let's see some questions on these two topics. So let's see, we have here to discuss these questions. So let's see. So question here, we have the effect of pH. So let's see this one question on pH. The researchers investigated the effect of pH values between pH 2 and pH 10.5 on the activity of bacterial lipase and hydrolyzing triglycerides at a temperature of 37 degrees Celsius. The results are shown in figure 2.2. So you see at this pH around 7, the rate is maximum. Okay, but as you increase pH or you decrease pH, the rate or the percentage activity that slows down. Okay, here at this pH, the enzyme activity is, percentage enzyme activity is the lowest, and then at this is even at lower, and you see at 7 it is highest, and then it is slowing down in this, and it is slowing down. So there is, when we increase the pH, there is a more percentage decrease in activity, and when there is a decrease in pH, there is less decrease in percentage activity. So these are the some points that you may be asked to write in your answer. With reference to figure 2.2, describe the effect of pH on the enzyme activity of. So this question begins with describe. In this case, you have to give a relationship, and you have to give a numerical code or the reference from an x-axis and from y-axis. So as I said earlier, you can take this value from here, like at 7 pH, the rate is this. You can take this is 100% activity. Okay, and then you can say that increase of the pH to this point, you can take this point. This has decreased to this point, that you can take value from here. And then similarly, when you lower down the pH value, so you see this has decreased to this value, so you can take these values to describe. So let's see. Increase of pH 2 to 7 and a decrease from pH 7 to, okay. So as we increase the pH from pH 2 to pH 7, the enzyme activity increases. And as we further increase the pH from 7 to 10, the rate decreases. This word increase and decrease is for the rate, and the other is, the changes. So except trend described as increase then decrease. Optimum or peak maximum activity 99% or 100% relative activity at pH 7. So this is another point. The maximum or optimum pH, and then the numerical value or the reference from the graph. Steeper decrease when the pH is increased from pH 7 to pH 10, and detail either side of the optimum. When you increase the pH or you decrease the pH, there is change in, or there is a decrease in the enzyme activity. There is less steep increase from pH to 7, pH 5 to pH 7. You can also refer to this point, like there are from this point to this point there is steeper increase, and from this point to this point there is less steeper increase. Okay, so 5 to 6 this is less steeper increase, and from 6 to 7 there is a more increase or more steep increase. Similarly, from this point to this point there is a steeper decrease, and from this point to this is a less steep decrease. So that's how you can make some comparisons in between the different parts. And then we have a pH 7 to 10.5. There is a steeper decrease between pH 7 and 7.5, less steep decrease between pH 7.5 to 10.5. Or activity pH 2 to pH 7, below 7, higher than activity after 8. You can make a comparison on both sides as well, except in alkaline, basic, or pH condition. So instead of writing the pH values from there, you can write acidic or basic, or you can write neutral conditions, etc. So except enzymes works better in acidic and neutral conditions, and enzyme works better in acidic than alkaline conditions. But enzyme activity throughout the pH range, you can throughout the range you can describe the enzyme activity, and then it is the data manipulated or the numerical reference that you can take up from an x-axis and y-axis, and then reference to partial denaturation. So this point is not actually needed. This is an additional point in a mark scheme. So as this question is about describing, and this gives us a reason. So this should be included when we write answers to explain the effect of pH. Okay, so we don't need to give this point, and probably that will not be accepted in the questions now. Let's see now. An experiment was carried out to compare the effect of pH on the activity of enzyme that was in solution and the same enzyme that had been immobilized on a gel. All other variables are kept constant. So we will discuss immobilized enzymes and free enzymes, and then we will come back to discuss this question. This is the effect of substrate concentration here. We have a substrate concentration here on x-axis, and we have rate of a reaction on y-axis. So now the question is, explain the results shown in figure 3.1. So you see, as we increase the substrate concentration from 0 to 20, there is steeper increase in the rate of enzyme action. Then if we talk about this further increase of substrate concentration from 20 to 25, there is a steeper increase in the rate of reaction. And further, if you look at this value from 25 to 30, the rate has become constant. Okay, so this is description. You have taken the values from an x-axis and you have taken the values from rate from the y-axis. You can pick up the values from here. So that would be describing. Okay, so as we increase the concentration from this point to this 20, the rate increases from 0 to this, okay, to maybe 14 point something. So this is description. This is describing this graph. You have to give reason why this increase of substrate concentration increases the rate to this point. Okay, so to describe, we give relationship and we give simply the numerical references, but to explain, we should give reasons why this enzyme activity is increasing. So more substrate, more collision between substrate and enzyme increases. So more ES complexes formed and higher rate. And from this point onward, from this point to this point, this is Vmax, 100% enzymes making ES complexes. Okay, and so substrate queued up waiting for their turn to bind into active site. Or you can say that the active sites of all enzymes are saturated with the substrate molecules, and they are all making the enzyme substrate complexes. So no more increase in the enzyme activity if even the substrate concentration is increased above 25 gram per dm cube. The units can be taken from here. Okay, so let's see these points. Up to substrate concentration of this 24 or 25, substrate concentration is that's another way. Though we do not have this concept of limiting factor in NAS, this is an A2, but you can also describe the concept of limiting factor to explain the effect of substrate concentration on the rate of enzyme action. We'll discuss this concept of limiting factor in another lesson. You can use it in your answer, but as I said, this is not part of NAS. This we will do in NA2. So let's see, from 24 or 25 to 30, substrate concentration is not a limiting factor. Something else is the limiting factor. So even if you do not know this limiting factor concept in NAS, that's okay. But if you know that, you can explain this graph on the basis of limiting factor. However, there are more points here. This comes in limiting factor. So we can active sites not filled up to 25 degrees to 25 grams per dm cube, and all filled up, they are all saturated with it. So enzyme working at its max, and reference to collision between substrate molecules and enzymes. So more are the substrate molecules, more will be the collision in between the substrate and enzyme. So this is up to 25 and this is above 25. So these are the 2 points that you must be able to write in your answer. This limiting factor is not essentially needed right now. Okay. Let's see, this is another question. In graph, the graph shows the effect of substrate concentration on the initial rate of enzyme catalyzed reaction. The enzyme concentration is constant. and we are increasing the substrate concentration and different substrate concentrations, we record the initial rate and then we plot it, and we had this graph, in this shape. Which statement about the graph is correct? Between R and S, the number of enzyme molecule is limiting the rate of a reaction. This is actually a concept of limiting factor here again. So you will have to understand the concept of limiting factor to answer this question. However, so as you are increasing the substrate concentration from this point to this point, from this point to this point, substrate is a limiting factor. Substrate is a limiting factor. And from this point to this point, substrate is not a limiting factor. So something else like enzyme concentration or temperature or maybe some other factor, that may be a limiting factor. So something else is a limiting factor. Okay, so between R and S, the number of enzyme molecules is limiting factor, so that's not correct. Between R and S, the number of product molecule is a limiting factor. No, the product is not influencing the initial rate of enzyme action at this point, so this is not correct. Between S and T, the number of enzyme molecules is limiting factor. Yes, that could be a limiting factor. So maybe this is correct, but without rejecting the option D, I cannot accept C. Okay, so I should go through this D as well and find the correct reason why we are rejecting the other choices. Between S and T, the number of substrate molecules is limiting the rate of enzyme action. So substrate is a limiting factor from R to S, but not from an S to T. S to T, it is not a limiting factor. So these three are not the correct choices, so C is a correct choice. So that's how we can, go through a selection and rejection of the choices, and we can find the correct choice. This is the effect of temperature. We have already discussed, then the substrate concentration is there too. So let's see. A student carried out an investigation into the effect of temperature on the rate of enzyme catalyzed reaction. At each temperature, the substrate concentration was measured after 10 minutes. All the other variables were kept constant. Which graph shows the effect of increasing temperature on the substrate concentration after 10 minutes? Okay. Which graph shows the effect of increasing temperature on the substrate concentration after 10 minutes? And this statement is important. At each temperature, a student carried out an investigation into the effect of temperature on the rate of enzyme catalyzed reaction. At each temperature, the substrate concentration was measured after 10 minutes, and all other factors or variables are kept constant. Okay, so a temperature where the enzyme activity will be the most, the substrate concentration after 10 minutes will be the least. Okay, so this is the temperature where the rate of enzyme action will be the most and the substrate concentration will be the least at this point. Why? Because the rate of enzyme activity will be the fastest at this point, and the substrate would more readily be converted to the product. So the substrate concentration will be the least at this point. So D should be the correct choice. What is wrong with, with this? At, when you carry out this experiment, this shows that substrate concentration is maximum at this temperature. So that's fine. But also at very high temperature, the substrate concentration should be higher. Why? Because the enzymes are denatured at this temperature, at high temperature, and so the substrate will slowly converted into product or will not be converted at all into the product. And this is actually this is where the temperature is an optimum temperature, and this is where the rate will be the maximum, but not the substrate concentration. Okay. So actually this might confuse some students, as we normally plot rate on y-axis and we plot temperature on x-axis. So this looks the same graph that the students are generally familiar with, but they don't, consider this y-axis has been replaced with the substrate concentration, or this rate has been replaced by the substrate concentration. So this is not the correct option. So this D is the correct choice in this case. So that's it for today. We'll continue with more questions and the Michaelis-Menten constant in the next class, inshallah. So thank you very much. See you tomorrow, inshallah.